Hello everyone, today in this video we are going to talk about magnetic field inside a toroid. So after this video you should be able to draw the magnetic field of a toroid and derive the expression for magnetic field inside the toroid. So to derive this we will be using Ampere's circuital law, which says line integral of magnetic field around a loop is equal to mu naught times the current threading through the loop. So this is a toroid. It is many tons of conductor in the form of donut. You can make a toroid by joining two ends of a solenoid. So this is a picture in which current is flowing in a solenoid, and if you consider the conductor at this point, it is taking the current towards the plane of the screen, that is away from you. So I can denote this by cross, and similarly at all these points the current is going away from you, so I'll denote it by cross. So at this point current is coming out of the screen, that is towards you, so I'll just denote this by a dot. So similarly for all other conductors this side, so this is dot. So you can represent a solenoid by a dot and cross picture. So now, in order to know the direction of magnetic field of a single conductor, we use right hand thumb rule. So it says that if you grab a conductor by right hand, if the thumb shows the direction of current, then the curling of forefinger shows the direction of magnetic field. Suppose the current is coming out of the plane of the screen, that is towards you. That time you can make the magnetic field which is anti-clockwise, and if the current is going into the plane, we can make the magnetic field around the conductor in clockwise direction. So we'll use this idea to draw the magnetic field of a solenoid. We'll understand the magnetic field of a toroid by using the concept of solenoid, because we can make a toroid by joining the two ends of a solenoid. So this is the picture of solenoid. So if you consider the magnetic field due to these two conductors, they will be in same direction, so they will get added up inside the solenoid. So if you consider magnetic field of these two conductors, they will be in same direction. So you can see the magnetic field inside the solenoid is in same direction, so it will get added up and make the strong magnetic field inside the solenoid. But if you consider just outside the solenoid, the magnetic field due to this conductor is going towards the left, and magnetic field due to this conductor is going towards the right. So they will cancel each other and you will not get any magnetic field outside the solenoid. So this is the picture of magnetic field due to a solenoid. So outside there is no magnetic field, inside there is magnetic field. Now we will make a toroid from a solenoid. This is a picture of solenoid. Now if you join the two ends of a solenoid, you will get a toroid. As we already know, inside the solenoid there was magnetic field, outside there was no magnetic field. So if you draw the magnetic field out here, so there will be magnetic field inside the toroid, just outside the toroid there will be no magnetic field. Now we will derive the expression for magnetic field. So to derive the expression, we'll consider a toroid, and we consider three regions. Region number one is just inside the toroid, and region number two is the region inside the toroid where magnetic field is there, and the third region is the region outside the toroid. So we'll consider a toroid with current I flowing through it, and we'll consider there are n number of turns per unit length. So we can write this formula: n is equal to number of turns divided by length. Now first we'll find the magnetic field in this region. So open space in the interior of the toroid. So we consider a loop with radius r1. This is our loop. So, and we'll consider b1 is the magnetic field out here. So line integral of magnetic field can be given by closed integral of b1 dot dl. So b1 is constant, so integration of dl is the length of the loop, that is 2 pi r. And if you use the Ampere circuital law on this loop, you will get line integral to be mu naught I. And if you put the value from here, so b1 2 pi r1 is equal to mu naught I. And as you can see, this loop is not enclosing any conductor, that means there is no current flowing through the loop, so I is 0. So if you put I is equal to 0 out here, you will get magnetic field to be 0. So that means there is no magnetic field in the open space at the interior of the toroid. So now we'll take the reason number 3, the open space at the exterior of a toroid. So this region. So we'll consider a loop of radius r3 and let b3 be the magnetic field out here. So line integral, I can write this, and the integration of dl is 2 pi r3, the circumference of this loop. So using Ampere circuital law, we can write line integral to be mu naught I. So this is the case, but out here you can see the number of conductor taking the current in upward direction is equal to number of conductor taking the current in downward direction. So the current crossing the loop in upward direction is equal to current crossing the loop in downward direction. So there is no net current, so I can write I is equal to 0. So if you put I is equal to 0 out here, you will get magnetic field to be 0. So there is no magnetic field outside the toroid. Now let us consider the region number 2, which is the region inside the toroid, and I am considering a loop of radius r2 and b2 be the magnetic field out here. Line integral of magnetic field can be given by closed integral b2 dot dl. So integration of dl is 2 pi r2, circumference of this loop. So according to Ampere circuital law, line integral of magnetic field can be given as mu naught times current flowing through the loop L2. As you can see, this loop will only enclose the conductor which is taking the current in downward direction. Only these conductors which are taking the current in downward direction. So now the number of conductor passing through this loop can be written as number of turns per unit length into the length of the loop. So this is n into 2 pi r2. So current threading the loop L2 can be written as the number of conductors into the current flowing through the toroid, that is I. So now if you put the value of current out here, then you will get b2 2 pi r2 is equal to mu naught I n 2 pi r2. So 2 pi r2 will get cancelled, so you are left with b2 is equal to mu naught In. So if you find the total magnetic field in all three regions, that is b1 plus b2 plus b3, then if you put the values, so you will get the magnetic field due to toroid will be mu naught times Ni, and which is same as the magnetic field due to a solenoid. So the magnetic field in the region with exterior or interior to the toroid is 0. So there will be magnetic field only inside the toroid. So this is everything written in one page, so we don't need to draw all the diagrams. So you can pause the video and copy the notes. There's the second page and the third page.